So I will, in the first part of the presentation, I will talk about the attention mechanism in natural language processing. And in the second part, I will talk about the transformer architecture and how they use the attention mechanism for like achieving the best result. The state-of-the-art results in natural language processing in many natural language processing tasks. So first of all, what is attention and where does attention come from? The concept of attention was first studied in computer vision. So to understand that, just briefly, let's suppose that we have an image, and we maybe with some tiny object inside it, and we will like to generate the caption of the image. So, like as humans, for solving this problem, what we do is to like roughly scan in the entire image, and then maybe we focus on the objects inside it and on the relations between the objects. So we can easily and efficiently actually also generate the caption. Okay, so produce the caption. An interesting question is there any any technique in computer vision similar to these human skills? And the answer is yes, there is. And it's also actually it's a well-known property, well-known features, like, but actually only recently this mechanism is also be applied to the natural language processing field. And we want to focus more on this application. For doing that, I will use a very, one of the most maybe studied tasks in natural language processing. That is the machine translation task. So what is the goal of the machine translation task is to translate sentences from one language to another language. So suppose that we have like this sentence, the man is tall, the English sentence, and we want to translate it in Spanish. Okay, so what we want to get is the el hombre es alto. So let's suppose that we don't know nothing about the transformers and the attention. So maybe the simplest way to do that is just to consider a very basic sequence model with two different RNN. So one for encoding the source sentence, and one for then decoding and get the final sentence. Sorry for the noise. So what we can see here is that the only like link arrow between the source RNN and the target RNN is this vector here, and this vector actually should contain all information about the source sentence in order to produce the like the target sentence. Okay. When this basic model were introduced, it was actually like a very breakthrough, a significant breakthrough in machine translation systems. But actually, he has these models have three major shortcomings, and these are first of all the NURBI context bias. Meaning that this vector here contains more information about the last time steps than the first time steps. Then there is another problem, that is the fixed context size limit, meaning that this vector is a fixed size vector, and of course when we have very long sentence, the sentence should be compressed in a fixed size vector. So this could be problematic. Okay, and third, the last one is slower sequential processing, because the RNN works sequentially. So for when you have to process like a word, you have to wait that the previous word is already processed. Okay, so we would like to overcome all these three shortcomings, but let's first start on the. We will focus on the first two. So what can we do for solving these two shortcomings? So what if instead, what if the target RNN, instead of just looking at the last hidden state of the source RNN, it can look at all the hidden state of the source RNN. This could be solved. Could be a solution for both the two shortcomings. But then we have to decide also how to combine this information, because we cannot just concatenate this information, because otherwise we will have maybe other kind of problems. So another good observation is that maybe for producing a single word here, maybe we just need only some of the hidden state of the source sentence, not all the hidden states. Maybe just the in this particular case. So these are the two main ideas of the attention mechanism. So suppose that we have like the sentence, the front door is red, and we want to get la puerta de entrada es roja. So as I said before, for producing the la word, we actually just need the word de of the source sentence. And for generating the puerta, the word puerta, we just need we just need to pay attention to the two words, the front and door of the source sentence. How can we formalize these two ideas in mathematical terms? So this is also called a cross attention, because it just is related. It links the encoder and the decoder. So it's also called the encoder-decoder attention. So so actually, if the standard target RNN can be, is written in this way, when we introduce the attention to the RNN, to this basic sequence-to-sequence model, we can write the target RNN in this way. So the only difference is the xi is replaced by the xi-ci, the concatenation of xi and ci, where this ci is the context vector related to this hidden state. And we can find this using this formula. So basically, we consider the hidden state H, and we match with all the source hidden states, and we produce some relations. And then we multiply these relations by the source hidden state, and we obtain like a context-based summarization of the source sentence. So what we exactly want, so the whole information about the source sentence needed for producing that particular word. Sometimes is also, sometimes people use also this other notation for, for the cross attention. It's actually exactly the same as before. The only difference here is this factor here, just because it's used in transformers. So basically, we have like a query, and so the hidden state is the query, and then we match with all the keys. We obtain these relations, and then we multiply these relations with the values, and we obtain the context-based summarization. So introducing the attention in this sequence-to-sequence model, we obtain like a small improvements when we have small sentences, and we obtain large actual improvements when we have like long sentence. Long is in this case is 50 or 60. But actually the problem it's, I mean, we still have the two problems that I mentioned before for very long sentences, so like 100 or maybe more, 1000, when we have 1000 words in a sentence. And also we have the problem, the third shortcoming, so the sequential processing. What we can do for solving also this third problem, since actually this problem is due to the RNN layers. So what if we just remove the RNN layers? This is the basic idea containing in the Attention is All You Need paper, where the authors introduced the transformer architecture, where we don't have RNN layers, but we have just 3 different kind of attention mechanisms. And so we have we encode the we have a first attention mechanism, which is the self-attention mechanism, in which each word can attend to the other words. Then we have the cross attention here. It's the same as we explained before, that we showed before. And then there is also this other attention mechanism, which is the masked self-attention, which is very similar to the self-attention in the encoder part, but it just can attend to the past, the previous words, because otherwise during the training we cannot, we cannot learn nothing. So this is how the transformers works in practice. These are the words. Okay. So just for recapping, we have three different attention mechanisms. So we already seen the encoder decode attention or cross attention. These are quite similar. So we will see now the self attention. So the self attention extends the cross attention mechanism, so that each sequence of hidden states also can attend to itself. So the source to the source and the target to the target. It's very similar to the cross attention. The only difference that now we have the query. It's the vector that we are considering, the source or the target, and we need to multiply by some projection metrics, and then it's exactly the same. So for each eye, this step, we have to compute the CI associated with it, and we can do this. We can do this independently. This computation can be done independently from the other J or high, let's say. So this is, we have opportunity for parallel computation. So the attention mechanism is not the only component of the transformer architecture. In each transformer layer, we have actually also the residual connection, just for prevent the vanish granted problem, maybe also, and we also have the feed forward layer. And usually we have 6 or more of these transformer layer in one one model. Okay, so some other details about the transformer architecture. So we say that when we encode the input sentence, we say that thanks to the attention mechanism, we can the attention mechanism takes into account the context of the word inside the sentence, within the sentence. But what about the position? It doesn't take into account the position, but we know that sometimes it's important, the position of the word with respect to the relative position of the word in the sentence, in many tasks. So this is solved using another encoding, which is called the position encoding. That is then some to the input embedding. Another property of the transformer is the multi-headed attention. Sometimes the CI, the context vector, doesn't contain important information. He loses some information, and essentially this is because we then like average out over the whole sentence. So the solution is to, the solution proposed by the authors is to like split the sentence that was the input sentence in many pieces, and then apply to each piece the attention mechanism, and then we just concatenate. So we don't average, but we concatenate the final output. So at the beginning of the talk, I say that that humans actually pay attention to important information in an efficient way. This is not the case for this kind of attention that I present today, because it goes quadratically, both in time and memory. So maybe we can do something, and there are many papers that try to solve this problem. And these are these are the main models that try to be efficient and fast. But actually, we would like to have like a small circle here, and we don't have it. But this is when you have use attention, you use transformers, you like spend time and memory, but this is for a good reason, because transformer actually performs very well. And here you can see that the comparison between the transformer and RNN and convolutional neural network for the machine translation systems, and also for many other applications, because as you will see with Gianluca, transformer can be applied to many fields, like sentiment analysis, or maybe also summarization. And in many of these applications, transformer outperforms the previous models. So this is all. Thank you for your attention. And if you have questions.
Right. If anyone has questions, please feel free to open your microphone and ask directly, or you can write in the chat and I can ask for you.
Or also at the end. I don't know if you prefer.
No questions?
Explained too well. Was true.
Yes, everything was explained very well.
Okay. If there are no questions, maybe I can share the screen and test the coding session.
Okay.
Yes,
So sure.
Yes, I cannot share.
I think first Claudia has to stop.
Stop sharing. Okay. Stop it. Okay.
Yes.
I didn't understand.
Okay. Okay, so everyone is seeing the share?
Yes.
Okay, so now we will introduce the most popular library used in Python in order to apply transformers model. And this library is actually called transformers, and is developed by a company named AGS SpA. So this library provides a lot of general purpose architecture, such as BERT, GPT-2, Roberta, XLM, Distilbert, and so on, for both natural language understanding and natural language generation. And it comes with over 32 pre-trained model in more than 100 languages. So this is very important because since transformers are huge models which requires a lot of computational power, we rarely start the training of a transformers model from scratch, but we will typically use a pre-trained model, and then we will maybe fine-tune on a specific task. So the agenda for the coding part will be the introduction to the transformers pipeline. Then we will see what is the tokenizer and the model in the transformers library. And then we will see an example of an end-to-end fine-tuning with the Hugging Faces transformers examples. So we can actually run transformers in Google Colab. So you don't need to have a powerful PC, a GPU, or install anything locally. And in order to do that, you just need to install the library. And you can actually do this in two ways. You can install it via pip install, or you can directly clone from the repository. So since today we will show a fine-tuning example using the end-to-end pipeline of transformers, these are present only if we directly clone from the repository. So we will do this in this coding session. Another things to do is to check if in Colab we have enabled the GPU, because this will make the fine-tuning faster. And in order to do that, we need to do this. We go to Edit, check the settings, and inside the settings, we can select the accelerator. So we will choose GPU. Then we will install the transformers. And another library which will be required is a dataset, and we will explain this later. It's still a library from the Hugging Face company. After we install all of our requirement, what we need to do is just check if the notebook is actually running on GPU. And to do this, we start by importing Torch. And I forgot to say, transformers works both with PyTorch and with TensorFlow. Typically, the default implementation are in PyTorch, but then there are also TensorFlow implementation, TensorFlow greater than 2.0. But by default, if we do not specify the library, it will be with PyTorch. So in order to check if the GPU is enabled, we can run torch.cuda.getDeviceProperties, and we can see that Google Colab has correctly assigned to us a Tesla K80 with 12 gigs of RAM. This is actually important because Google Colab kind of assign randomly the GPU. So maybe sometimes we can have 12 gigs GPU, sometimes a 16 gigs GPU. If we are unlucky, maybe even an 8 gigs GPU. And we need to check this before, because when we are doing fine tuning, maybe we can increase or we should decrease the batch size in order to not get out of memory. So the first things we will show about transformers is the pipeline object. The pipeline object is actually the easiest way to use a pre-trained model on a specific task. And it provides out of the box different features and different natural language processing tasks. In particular, we can have sentiment analysis, which tell us if a sentence we are examining is positive or negative. Then text generation, so we can kind of input a prompt and the model will start generating text which is coherent with what we entered before. Then named entity recognition, which is a task in which we input a sentence and label each word with the entity to represent. So for example, a person, a place, and so on. Then we will have question answering, which we will see in an example. And it's a task in where we provide a context, which will be our knowledge base. It can be, for example, a paper, a document, and so on. And we can ask questions on this document in natural language, and the model we will answer based on the information given in the document. Then filling masked task, in which we given an input text with some masked words, and then the model will automatically fill the blank spaces. Summarization, in which we will summarize a long text into a smaller one. Translations and feature extraction. So we will start by importing the pipeline object from transformers, and we can instantiate that by calling just two parameters, which will be the string regarding the task we want to use. So in this example, we can use a sentiment analysis, and we can specify which model we want to use. So we instantiate it. The library will automatically download the model from the model hub of Hugging Face, and we can just use it in one simple line of code. So here we want to do sentiment analysis. So we are input inside the classifier one string, which is we are very happy to learn about transformers. And the model will automatically given us the output, which is a rating, in this case, based on stars from 0 to 5, which tell us how good, how positive is the sentence. So in this case, we have a very positive sentiment, so the model output 5 stars. So we may ask you when the model was downloaded. Well, the Hugging Face company given us the so-called model hub, which I will show you now. You can see the new tab opened.
Yes.
Okay. So this is the model hub, and inside this page we can look for all the model that the community and even some NLP company have trained, and we can search for a lot of different tasks, a lot of different libraries, datasets, and languages. So, for example, we want a question answering model. We can select question answering. Then we want this model question answering also in English. And automatically the hub will filter us all the output, and we can select the model that we want. What we need to do then is just to click on one. We can take this string and put inside here. Then automatically the transformers pipeline will download this model, and we can start using. So this is very, very useful if we need maybe to do some specific task. The first thing to do is actually looking in the model hub and see if there is already some pre-trained model that solve our problem. But now we can actually go a little bit deeper and instantiate the model and the tokenizer with the from pre-trained method. in this way, we don't have the pipeline which wrap everything together, but we can split the model into two pieces, which is the model and the tokenizer. So we can import it by using these two classes, auto tokenizer and auto model, in this case for sequence classification, because sequence classification is the task that we want to solve, and sequence classification is, for example, sentiment analysis. And we will use auto model because with auto model, the library take cares of which model we are instantiating. So for example, we can use a BERT model, a T5 model, an XLM model, different architecture. The auto tokenizer and the auto model detect automatically which architecture we are importing and select the correct tokenizer and the correct model. And now we will look at what is the tokenizer and what is the model. Well, actually, what the tokenizer do is just the pre-processing and the conversion of the string we are given in input into a vector. So before feeding our data inside the model, we actually need to tokenize it. So for example, we have this phrase, the cat sat on the mat, and the tokenizer will split into tokens, which is actually the single splitted string, which will be then converted into a tensor and feed into the model. So we can see the tokenizer in action. We input inside the tokenizer our phrase, and then we have this method, which is convert index to tokens, which will give actually the output of the tokenizer. And we can see how the tokenizer split the sentence. And we will also see that typically, this is depending of the model. We have at the beginning and at the end, the so-called special tokens. And these special tokens help the model to understanding better the sentence. So in this case, we have the CLS token, which indicates the start of a sentence, and the SAP token, which indicates the end of the sentence. There is also another case in which we can actually input some tokens that are not inside the vocabulary, are not trained inside the model. So the model doesn't actually know how to split this word. And this is an example. So if we input inside the tokenizer, do you know how to split the word precipitevolissimevolmente? Well, what the tokenizer do is actually split in strings the word that he knows. And then when he encounters some word that he have not in the dictionary and he doesn't know how to split, he will actually split into some subword by prepending some tags. And this is done because the model is trained to understand that the token that start with these tags are actually not single word, but are derived from some unknown masked tokens. And this actually help the model to understand this. Then, after we have explored the tokenizer, we can see what actually the model do. And the model take the output of the tokenizer, which will be actually our inputs. And this is a dictionary with some information other than the tokens. But what we need to do is just to expand the input of the tokenizer inside the model, and the model will give us the output, not expressed like the pipeline in a clear way like this, but expressed in output logits. So what we will have here is the model final activation logits. And we actually need to know in advance what these logits mean. So in this case, we are using the same model of before. So we know that each logits represent a rating of the word, of the sentence. So the sentence is the same. We are very happy to learn about transformers. What we need to do actually is to calculate the argmax of the output logits, and in this case is the last element, which corresponds to the pipeline output 5 stars. After this, we can actually see some of the default pipelines of the transformers. There are many of these and are all present in the documentation, but now for the sake of explanation, we will show only two, which is sequence classification and question answering. So as we've seen before, sequence classification is the task of classifying sequences according to a given number of classes. So before we have 5 stars, but we can actually also have 2 classes, for example, positive or negative. So if we start again from the pipeline and we instantiate the object, and you can see that here I didn't specify the model, so there is no model here. And when we do this, the library automatically select the default model. This default model is being downloaded, and then we can call the object NLP with the sentence and extrapolate the answer. So we have here 2 sentences, I hate you and I love you. I hate you as a negative sentiment with 0.99 score, and I love you a positive sentiment with 0.99 score. Another example of task is the extractive question answering. So in the extractive question answering, we are given to the model a context, which is our knowledge base, and asking some questions. So in order to instantiate the question answering, we just type question dash answering inside the pipeline, and we can create again the NLP object. Then we need 2 inputs in this case, which is the context and the questions. So this is the context, and the context represents, as I said before, the knowledge base. So this is a text which explains actually what is extractive question answering and how this task works. And our question is actually, what is extractive question answering? We pass the 2 parameters inside the NLP object, and we get the result. And the result is this, the task of extracting an answer from a text given a question. And this is actually the answer of this question given this context. And we also have a start index and a end index, because this model, in order to work, extract actually the start and the end passages of the context by taking the first token and the last token. So we can see that this phrase is exactly this phrase. So the model search for an exact passage of the context which answer this question, is not generating the question from scratch. In order to do this, there are others model, but we will not see here. But for example, there is some other model like Albert, which can generate from scratch new answers. But what can happen? This is the basic task of transformers. Maybe we have the need of some specific application in which we have a specific domain where the model is not trained. So in order to do this, in order to have good performance on some very specific domain, what we need to do is to make a fine-tuning of our model. So inside the repository, there are actually some end-to-end script written from the transformers maintainers, which actually allow us to fine-tune a model from scratch with running just one script. There are actually two ways to fine-tune a model, and we can use this script, and we can actually instantiate the model with TensorFlow Keras trainer and write our training loop. So, as an example, we will fine-tune a plain BERT model, so a BERT model trained on a masked language model on the SQUAD dataset, which is the Stanford question answering dataset. And the first things to do, since using a dataset or creating a dataset from scratch is very time consuming, is look inside the Datasets Hub of Hugging Face for maybe a dataset that cover our problem. As I showed before, in fact, I installed this library, pip install datasets, which is actually another library maintained and developed from the Hugging Face, which is like just like the model hub is a dataset hub. So inside this dataset hub, we can look for a lot of different datasets uploaded both by company and by users, which can cover most of the natural language processing tasks. And also these are available in multi-language, tagged from different tasks and size, and also license. So for example, maybe we want to fine-tune our model for question answering, and we need the SQUAD dataset. We actually need to search from the SQUAD dataset, and this is actually the official SQUAD dataset developed by Stanford. We can see some information regarding the dataset, like for example, its size, its structure, and so on. And when we are happy with what we have found, we can actually just use it directly inside the script. So if we open the repository of the transformers, we can see that inside the main folder, there are an example folder, which is divided by library. So we have a PyTorch and a TensorFlow folder. And inside that, we can see that there are end-to-end script examples for fine-tuning, from training from scratch, and so on, divided by task. So in this case, we can see that we have a folder which cover our problem, which is fine-tuning on question answering. And actually the file present here is called run QA. So what we need to do is just run this file, this script, selecting some argument. For example, we can select the model name or path, and this can be a model name will be automatically a model which is present inside the model hub. So if we indicate a model name, it will be downloaded from the hub. Or a model path, because maybe we have trained some model, we have hit locally in a folder, and we want to use this as a starting point. So we can just enter inside here, we can enter the path of the model. Then the dataset name, which is the corresponding name inside the dataset hub, and some other parameters which is different regarding the task. but all the argument can be explored inside by looking inside the script. So here, for example, we will do train, we will also do evaluation. We can select the batch size, and this, as I said before, is important because if we are assigned inside Colab GPU with low memory, maybe we need to reduce this dimension, or if we were lucky and Colab assigned us a GPU with high memory, we can increase this and speed up training. Then we can set, for example, the learning rate and the number of train epoch. So this is very important parameters because when we are doing fine tuning, we typically do not want to have a very large number of epoch because we are starting with a model that is already trained on language modeling. And what we need to do is just to tweak a little bit the weights in order to make the model good for our specific task. But if we use too much learning rate and too much epochs, what we risk is to have a model that will lose some information about the pre-training part, and actually the performance may be worse. Then we can select other parameters, but it's not very interesting, and the output direction in which we want to put our fine-tuned model. We will start, and when the fine-tuning starts, I will suggest to look at the first line of the debugging part, which can actually tell us if the notebook is correctly using the GPU. So in this case, we can see that the model has opened successfully the CUDA library. So we are actually training on a GPU. If we will see on the log some information regarding the architecture we were using, and we can check that actually we are training a Distilbert model. So here it will tell us that the architecture is correct, is the Distilbert model, and we can just start training. So we run the script, we wait for the output. And then when the fine-tuning is done, and since we select do evaluation, what we will see is the metrics, so the performance of our model, which is a recap of the number of epoch on the number of samples we have done evaluation, and the scoring. So the scoring, of course, will be different regarding of the task. Here in question answering, we typically use two scores, which is exact match and F1 score. F1 score is always bigger than exact match because maybe they can be the same, but it's very rare. Exact match tell us that the model, the question answering model, exactly extract the start and the end of the questions, of the answer regarding the label, while the F1 score is tell us how much superposition there is between the label and the actual answer. Because, for example, here our answer is the task of extracting an answer from a text given a questions, but maybe the label can start from this. So this is still a good answer, but maybe it's not the exact answer that the labeler choose. So we need to know for question answering at both metrics. And for me, I've finished my part. So I hope you like this introduction to transformers. You can explore a lot. There are there are a big number of tasks and features from this library. This is just an introduction, but I think it will be enough for you for getting started and start to use this library from